Hello, you're watching Armando Hasurungan, biology and medicine videos. Please make sure to subscribe, join the forum and group. For the latest videos, visit Facebook Armando Hasurungan without a space. Like, ask questions, answer questions, and please post some of your artworks or anything interesting. And you can change the settings to original or a HD, I think original, for better graphics, which I highly recommend. And this video is going to carry on from the last video, which concentrated on the regulation of glycolysis and gluconeogenesis, concentrating on the specific second pathway between fructose 6-phosphate and fructose 1,6-bisphosphate. So as we know, fructose 6-phosphate converts to fructose 1,6-bisphosphate in glycolysis, and fructose 1,6-bisphosphate converts to fructose 6-phosphate in gluconeogenesis. Now, from fructose 6-phosphate to fructose 1,6-bisphosphate, the enzyme used is phosphofructokinase 1, and phosphate is obtained from ATP. From fructose 1,6-bisphosphate to fructose 6-phosphate, the enzyme used is fructose bisphosphatase 1. Now note the 1 in each of these enzymes. And in this reaction, fructose 1,6-bisphosphate is hydrated to remove the phosphate as inorganic phosphate. So fructose 1,6-bisphosphate will essentially proceed to glycolysis to make more ATP. And fructose bisphosphatase 1 will make more fructose 6-phosphate for gluconeogenesis to make more glucose. So let's go over what regulates these two enzymes again. We have ATP, which will inhibit phosphofructokinase 1 because we don't want to promote glycolysis to make more ATP because we already have a lot of ATP. However, ADP will stimulate phosphofructokinase 1 because high amounts of ADP need to convert to ATP through glycolysis. AMP will inhibit fructose bisphosphatase 1, but it will stimulate phosphofructokinase 1 for the same reason as ADP would stimulate phosphofructokinase 1. And also randomly, citrate will inhibit phosphofructokinase 1. And now most importantly, fructose 2,6-bisphosphate, a product, will inhibit fructose bisphosphatase 1 but stimulate phosphofructokinase 1. So fructose 2,6-bisphosphate, a product, will promote glycolysis but inhibit gluconeogenesis. So what is fructose 2,6-bisphosphate? Let's have a closer look. So fructose 6-phosphate in glycolysis, so normally, it will convert to fructose 1,6-bisphosphate but fructose 6-phosphate can also convert to fructose 2,6-bisphosphate. Fructose 2,6-bisphosphate gets its phosphate from ATP. The phosphate is on the carbon number 2. So the difference is fructose 1,6-bisphosphate, the phosphate is on number 1, but fructose 2,6-bisphosphate, the phosphate is on number 2. And the enzyme used to convert to fructose 2,6-bisphosphate is phosphofructokinase 2. And fructose 2,6-bisphosphate can then be hydrated to remove the phosphate from carbon number 2 and become again fructose 6-phosphate by the enzyme fructose bisphosphatase 2. Now you might have realized that between fructose 6-phosphate and fructose 1,6-bisphosphate and between fructose 6-phosphate and fructose 2,6-bisphosphate, the name of the enzymes are the same, just one has number 1 and the other has number 2. Keep that in mind. Now fructose 2,6-bisphosphate is a product, not an enzyme, and it essentially promotes glycolysis and inhibits gluconeogenesis. Interestingly enough, as the regulation between fructose 6-phosphate and fructose 1,6-bisphosphate is controlled by fructose 2,6-bisphosphate, there are other forces controlling the regulation of fructose 2,6-bisphosphate. Now I would like to portray this in a diagram. So we know that high amounts of fructose 2,6-bisphosphate will stimulate glycolysis, but it will inhibit gluconeogenesis. Now, this egg-looking thing is the enzyme which makes and breaks fructose 2,6-bisphosphate. As you can see, it is phosphofructokinase 2, which makes fructose 2,6-bisphosphate bonded with fructose bisphosphatase 2, which dephosphorylates fructose 2,6-bisphosphate. Now, PFK2, phosphofructokinase 2, is active as indicated by the shining strokes, and fructose bisphosphatase 2, FB-PACE2, is inactive. FB-base2 is inactive because the whole enzyme is not phosphorylated, so it contains a hydroxyl group, as you can see. Now, this stimulates phosphofructokinase 2, which increases the synthesis and conversion of fructose 2,6-bisphosphate and therefore stimulating glycolysis. Of course, if fructose 2,6-bisphosphate concentration are too high, this egg enzyme will undergo phosphorylation by another enzyme, CAMP-dependent protein kinase. And the egg will get the phosphate from ATP. I am using an egg as an analogy, by the way. So just to pause here, I don't know if you remember cyclic AMP-dependent protein kinase from the last video, but here its main role is to phosphorylate this double egg enzyme to inhibit glycolysis. So it will phosphorylate, give a phosphate group. And same in the previous video, it also inhibits glycolysis from phosphoenolpyruvate to pyruvate. Now the phosphorylation of this egg enzyme will is stimulated by a hormone, glucagon. So this egg enzyme, but it will stimulate by glucagon, which is a hormone. And as you may know, glucagon will promote gluconeogenesis and basically inhibit glycolysis. Now the phosphorylated egg enzyme obviously causes FB base 2 to be active. So fructose bisphosphatase 2 to be active and inhibit phosphofructokinase 2. And now the phosphorylation of the egg, remember, I'm only using an egg as an analogy, will mean that phosphofructokinase 2 will become inactive and fructose bisphosphatase 2 will become active. When fructose bisphosphatase 2 is active, it means that fructose 2,6-bisphosphate levels will drop because fructose bisphosphatase will convert fructose 2,6-bisphosphate to fructose 6-phosphate. Decreased amounts of fructose 2,6-bisphosphate will decrease glycolysis and stimulate gluconeogenesis. And then again, if fructose 2,6-bisphosphate product levels drop too low, the egg enzyme will be hydrated to remove the phosphate. And this is done by the enzyme phosphofructophosphatase. Phosphoprotein phosphatase. So the phosphofructokinase 2 can be active again, and fructose bisphosphatase 2 will be inactive again, and bringing fructose 2,6-bisphosphate levels back up. And the hormone insulin will stimulate phosphoprotein phosphatase because insulin increases the activity of glycolysis, remember. So that was, okay, that was detailed. Let's just go over the overall diagram now. So from fructose 6-phosphate, in glycolysis, it will convert to fructose 1,6-bisphosphate. This is in glycolysis under normal situations. So fructose 1,6-bisphosphate. And this is done by the enzyme phosphofructokinase 1. So fructose 1,6-bisphosphate can then convert in gluconeogenesis back to fructose 6-phosphate. So between fructose 6-phosphate and fructose 1,6-bisphosphate, the enzyme used is phosphofructokinase 1. And the reverse is fructose bisphosphatase 1. However, fructose 6-phosphate can also convert to fructose 2,6-bisphosphate, which is another product, right? And this is done by the enzyme phosphofructokinase 2. And then it can go back to fructose 6-phosphate by the enzyme fructose bisphosphatase 2. See the same naming, except just different numbers? So fructose 2,6-bisphosphate will stimulate phosphofructokinase 1 and glycolysis. So it will stimulate glycolysis, making more ATP. However, fructose 2,6-bisphosphate will inhibit fructose bisphosphatase 1. So it will inhibit gluconeogenesis. So there's a regulation for fructose 2,6-bisphosphate between the enzymes. So phosphofructokinase 2, if it's active, it will promote fructose 2,6-bisphosphate conversion. However, if fructose 2,6-bisphosphate levels are too high, the enzyme will be phosphorylated, so to add a phosphate on it, and glucagon will stimulate this reaction, and also cyclic AMP-dependent protein kinase will also stimulate this reaction. However, of course, if fructose 2,6-bisphosphate levels are too low, phosphofructose bisphosphatase 2 will be dephosphorylated by hydrating it and removing the inorganic phosphate, and this will cause it to return to fructose phosphofructokinase 2. And now insulin promotes this reaction. And remember that fructose bisphosphatase 2 and phosphofructokinase 2, the enzyme used between fructose 6-phosphate and fructose 2,6-bisphosphate, are actually connected. So if one is phosphorylated, it will promote gluconeogenesis. If one has a hydroxyl group on it, it will promote glycolysis. Please keep that in mind. I hope that was quite simple. That diagram is actually really good. I'll probably keep looking at that and trying to understand that. Please comment, like, and subscribe if you must. Actually, please. Thank you.